All right, section 6-6 is on the derivative and integral practice. And again, the objective of this section is to differentiate and integrate functions involving logarithms and exponentials. And you worked with that throughout the chapter. In fact, you got a nice review of that in the first half. And there's another set of antiderivatives that we need to talk about. And so we're going to tackle that right here. And in particular, we want to work with your trig functions and finding their antiderivatives. Now that we know the rule for the integral of a reciprocal function, turns out we can actually find all 6 of our trig functions and their antiderivatives. So the integral of tangent of x. Let's go through and actually find what the antiderivative is equal to. And to do that, we're going to rewrite this using the quotient form of tangent. Tangent can be rewritten as the sine of x over the cosine of x dx. And definitely looks like we made this more complex as we just introduced another trig function, but what really happened is we got this into a form now that we can actually find the antiderivative of. And we're going to use a u substitution to do this. We're going to let u be the denominator, the cosine of x. And then du turns out to be derivative of cosine's a negative sine of x dx. And you can see I have a sine of x dx. I just don't want the negative there, so I'm going to slide him over to the other side to get negative du is equal to the sine of x dx. And now we're ready for our substitution. So this becomes, instead of sine of x dx in the numerator, it's a negative du divided by, instead of cosine of x, that's u. And we can go ahead and rewrite this. You can leave it in this form here and integrate it, but if it's helpful, sometimes pulling out the negative out front, the constants come out front is one of our properties. If you want to write it as 1 over u du, if that's easier for you to see the property, then do it that way. But that's your reciprocal function, the integral of a reciprocal. We learned in this chapter that that's our natural log function. Whoops. This is equal to the opposite of the natural log of the absolute value of u plus c. And finally, replace u with what it's equal to. We said that u is equal to the cosine of x, so it's a negative natural log of the absolute value of cosine of x plus c. Now that's one form that you could use to remember this property. However, we're going to rewrite it and put it in another form, and I'm going to definitely recommend that you do the same thing and remember the second way we're going to write this. If you have this constant out front, if you want to, you can think of this negative out front as actually being a -1. And so that -1 I can actually move and put as a exponent here. That's one of our properties of logs. So I can rewrite this as the ln of the absolute value of cosine of x raised to the -1 plus c. Of course, raising something to the -1 is the same as the reciprocal of that quantity. So I can rewrite this as the ln of 1 over the absolute value of the cosine of x plus c. Of course, if I have the absolute 1 over the absolute value of cosine of x, that's the same as the absolute value of the whole quantity here, because 1 is the same as the absolute value of 1. So I can rewrite this as the absolute value of 1 over cosine of x, that whole quantity, plus c. And 1 over cosine is better known as secant. That's our reciprocal property. So the ln of the absolute value of secant of x plus c. And that's the way that I'm going to recommend that we learn this. That the antiderivative of tangent is the natural log of the absolute value of secant of x plus c. And the reason for that, if I can recall my rules for the derivatives, I know the derivative of tangent, let me just write that over to the side here, derivative of tangent is equal to secant squared of x. Notice that the derivative of tangent involves the same trig function as the antiderivative. So the nice thing about writing it in this form is if I can remember the derivative properties, it will help me remember the antiderivative property. So derivative of tangent is secant squared. The antiderivative is the natural log of the absolute value of secant of x plus c. Same trig function. In fact, we can do that for all of the other 4 trig functions that we have not worked with yet. You obviously already know the antiderivative of sine and cosine. Let's take a look at secant. The integral of secant So to find the integral of secant, we actually have to multiply by a clever form of 1. This one isn't quite as obvious when we start out with, but you're going to see something nice is going to happen here in a second. But I want to take and multiply this by the quantity secant of x plus the tangent of x divided by the secant of x plus the tangent of x. Okay? Again, that probably doesn't look like an obvious step here, but when I multiply the secant through the numerator there, I'm going to end up with the integral of secant squared of x, secant times secant, plus the secant of x times tangent of x. And that's all divided by the secant of x plus the tangent of x dx. And I'm going to again use a u substitution on this thing. We're going to let u equal the denominator now. So u is equal to the secant of x plus the tangent of x. So du turns out to be derivative of secant is secant times tangent. And the derivative of tangent is secant squared. That, of course, is all multiplied by dx. I'm going to squeeze that in there. And notice that's what the numerator is. It's written in the other order, but the same thing. So this becomes the integral of du over u. That's the same function we just integrated on the last slide there. That's our natural log function. It's the ln of the absolute value of u plus c. So this is the ln of the absolute value of u. U, again, remember, was secant plus tangent. And there is our antiderivative. Now, in this case, we don't need to rewrite this, or I'm not going to rewrite it at all, because this form actually, as it turns out, is really nice to remember. And again, we already actually did this up above here, but I'll write it down just to refresh your memory here, that if you were to find the derivative of secant, that's equal to secant times tangent. So again, the nice thing about using this form here, or keeping it in this form, is that the derivative involves secant and tangent, and the antiderivative involves the exact same trig functions, secant and tangent. So again, if you remember your rules for the derivatives of secant, it'll help you remember the rule for the antiderivative of secant. All right, so here are the 6 properties here then. These are in your book there as well, but the first 2 you obviously know. The integral of sine we already knew was the negative cosine of x plus c, and the integral of cosine is sine of x plus c. I've arranged these in columns like this because we've seen with the rules for derivatives of your trig functions and inverse trig functions, that there's a relationship between the derivatives of sine, tangent, and secant and their cofunctions. Same is true with the inverse trig functions. And the same is true here with the antiderivatives of these trig functions. So over here on the left, we have the integral of sine of x dx is equal to negative cosine of x plus c. If I replace each trig function in there with its cofunction and take the opposite of the answer, I end up getting the second property here. So replace sine up here with its cofunction, that's cosine, and replace cosine here with its cofunction, that's sine, and take the opposite of the answer. This one is a negative cosine on the left, so this becomes a positive cosine on the right, or positive sine on the right. We get that property. Look at tangent. The integral of tangent of x dx we know is now equal to the natural log of the absolute value of secant of x plus c. We just went through and derived that. If you take and replace each of the functions in there with its cofunction, you get the other property. So replace tangent with cotangent, replace secant with cosecant, and take the opposite of that answer. So you have a negative out front. And finally, for secant, the antiderivative of secant we just found out was the natural log of the absolute value of secant of x plus tangent of x plus c. And if you want its cofunction, replace each of the trig functions in here with its cofunction. So the integral of secant becomes the integral of cosecant. And instead of the natural log of secant plus tangent, it's the natural log of cosecant plus cotangent. And you take the opposite of that answer, so it's negative. Again, if I remember the 3 that are over on the left side, that helps me remember the other 3 that are over on the right side. And here's that little property that we've now used actually several times here, like I said, for the derivatives of your trig functions and inverse trig functions, and we find it applies again so nicely for our antiderivatives as well. To find the integrals of your cofunctions in the right column, replace each trig function in the left column with its cofunction and take the opposite of the result. It's a very nice way to remember those. All right, let's try a couple of examples here then. They didn't give us any examples in the book, so I'm just going to give you a couple of examples here for us to try. The first one is the integral of tangent of 5x dx. So again, use your property here, but I'm going to just, to help us out a little bit, if you get stuck with the 5 that's in there, then use a u substitution. I'm going to let u equal 5x, so then du is equal to 5 dx. So 1/5 du is equal to dx. And now let's substitute that in. So we end up with the tangent of u. And instead of dx, it's 1/5 du. If you like pulling those constants out front, then it's 1/5 the integral of the tangent of u du. And now use the property that we just learned. We just learned what the antiderivative of tangent is. Again, the derivative of tangent is secant squared. So the antiderivative involves the same trig function. Oops, let me get rid of that integral sign. So it's the natural log of the absolute value of secant of u plus c. So that turns out to be 1/5 the natural log of the absolute value of secant u is equal to 5x plus c. There is our result. There's our answer. Let's take a look at one more example here. This one is for cosecant. Again, I'm going to use a u substitution for this. You don't have to, but if it helps you with those constants there, then do so. So 2x minus 3 will be u. Du turns out to be 2 dx. I'm going to get rid of the 2 from that side, so 1/2 du equals dx. And now we're all set for our substitution. So this becomes the integral of the cosecant of u. And for dx, we replace that with a 1/2 du. Again, if you prefer putting the constant out front, then do so here. So 1/2 the integral of cosecant of u du. And now we are all set for our integration. Again, we just talked about the rule there for the integral of cosecant, which, by the way, in the book there, if you look, they show you a couple ways to remember it. Again, I would suggest the way that I showed you, because I think that's the easier one to remember, and that little property we've talked about. But I guess it's technically up to you on which way you're going to remember it. But anyways, the derivative of cosecant involves cosecant and cotangent, and so it's a negative cosecant cotangent. So this is a negative natural log of the absolute value of cosecant of u plus the cotangent of u, and then plus c. I need to put a parenthesis there. Plus c at the end. And now replace u with what it's equal to. And so we end up with a negative 1/2 out front, natural log of the absolute value of the cosecant of 2x minus 3 plus the cotangent of 2x minus 3, and then plus c at the end. There is our antiderivative of that function. All right, that's as far as we're going to go for this second half of this section.